So this is golden video because there are many reducing agents. In that strong, weak, everything are there, but there is no reducing agent can reduce all the functional groups, which means every reducing agent works with at specific conditions. So the major principle for this is selectivity of reducing agent. This depends on these factors. So every reducing agent won't function with one specific factor. So you supposed to know these four properties. See, some will produce H minus ion and reduce the functional groups. Some need specific acidic or basic medium so that it can reduce functional groups. Some cases even the nature of functional group also matter, which means stability and reactivity of the functional group. And some cases even resonance, nature of bond, everything matters. So that is why different principles are used for different reducing agents. So that is why mostly every student confused in this area, and these things not teach in classroom also in most of the places. That's why don't stop watching complete video. Surely it will help and it will worth for your studies. So the next the same thing in different manner we can discuss. So here reducing agent means generally it will produce H minus. Weak hydride, if the reducing agent can give H minus ion very slowly or weakly, those reducing agents can reduce aldehyde and ketones to respective alcohols. Suppose example for this is NaBH4. Suppose if the reducing agent can give H minus ion very effectively, that which means you take example of LiAlH4. In this case, two strong electropositive metals are there. These electropositive metals give electrons to H minus, so that the H minus easily come out from this. But in case of NaBH4, these two are not strong electropositive metals. Sodium is strong, but boron is not strong electropositive metal, so it will not give electrons easily to H hydrogen. So H minus can come very weak manner as comparatively LiAlH4. So strong hydride reducing agent can reduce everything. Here also there are some exceptions, or some, it's not exceptions, it's matter of conditions. Even alkenes doesn't reduce with LiAlH4, and some alkenes will reduce. I will give you everything A to Z, all the conditions, exceptions, properties, why it will be, why not it will be, all those things. So coming to the next one, surface hydrogen. Suppose you might see some alkene or alkyne reduction. So that happens in presence of which one? Some metals, D block metals, PD, PNi, Zn, PT, all these things. So those all will work based on the absorption phenomena. Means even surface also matter, or what exactly it is we'll discuss in the coming things. So acidic metal reduction. So you take examples of Williams Clemmensen reduction and Wolff-Kishner reduction. There we can understand specific reaction mediums are required. Suppose Wolff-Kishner reduction means you take KOH, Clemmensen reduction means you take HCl. So specific mediums matter in that. So how it will work, why specific medium, what are the sensitivity things in that, everything we'll discuss. Generally this acidic metal reduction is applicable for Clemmensen reduction. So electron transfer, some cases reduction happens even by accepting electrons. It's not only always addition of hydrogens, some cases removal of oxygen, some cases adding electrons. So generally nitro compounds are amine related. All the oxidized form of nitrogen happens through electron transfer medium, students. Now we are going to discuss one by one reducing agent, what work it will do, all those things. So this is the overall conclusion about this is every reducing agent follows some specific method to reduce it and needs certain mediums or certain things to make proper reduction process. Coming to first reducing agent is NaBH4. NaBH4 means sodium borohydride. So this can reduce aldehyde and ketones, because aldehyde and ketone case, the C double bond easily break and get positive and negative charge for longer time. The reason is due to electronegativity difference between carbon and oxygen. So the electrophilicity of carbon means positive charge over the carbon stays longer time. So even weak hydride donors also can reduce aldehydes and ketones. That's the reason. But in case of ester, carboxylic acid, amide or alkene, suppose you take ester 2 stable. The reason is ester, if you take, this is the group RCOOR. Here the lone pair of electrons keep on moves to C double bond O group, so that the positive charge over this will be unstable. Because of that, H minus, the one which give H minus very lightly, cannot go and attack easily. Before that itself resonance will happen. That's why carboxylic acid or esters, mainly esters will happen. Now, like why NaBH4 cannot reduce esters means due to resonance in simple manner. Coming to carboxylic acids. Carboxylic acids, NaBH4 is like basic nature, and acid is, carboxylic acid is acidic nature. Between them, acid base reaction takes place instead of reduction process. Coming to amide. Amide means even this is also resonance stabilized as like ester. And alkenes, you can take RC double bond O NH2. Here also same reason, so the resonance will happen faster. And alkene case, alkenes are not polar bonds, which means C double bond C is purely covalent compound, because no electronegativity difference between the carbons. So this bond will not break easily to make carbon plus. So that's why polar non-polar bonds cannot be reduced with NaBH4, because NaBH4 cannot give H minus effectively, and it is mild and selective reducing agent. So why it is like that? Same reasons what I explained. Just you can look at this. NaBH4 give weak hydride ion, works in polar protic solvent. Very important point. Wherever we use NaBH4, beside we use H2O, because H2O helps to produce H minus ion from NaBH4. If you take LiAlH4, we should not use H2O here. In that case, here we use H2O. Just it helps to produce H minus ion little more effectively. Can attack only high electrophilic carbon atoms. That's what. The formed positive charge should stay for longer time, then only it will work. Otherwise it won't work. So the conclusion, JEE exams or NEET exams, what they ask students, NaBH4 selectively reduce aldehydes and ketones only. Coming to sodium borohydride. So it is mild reducing agent, same thing, reducing aldehyde and ketones only. Doesn't reduce carboxylic acid, esters or amides or nitriles. And explanation for this, NaBH4 provide weak hydride ion, same reason. Just to get full clarity about NaBH4, I am doing this. Carboxylic acids, esters are resonance stabilized and less electrophilic because of resonance. So NaBH4 cannot reduce them. And here also same thing, it will reduce only aldehydes and ketones. Hope it is clear, students. Coming to the next, LiAlH4. LiAlH4 reduce everything, but it won't reduce non-polar alkenes. That also we can discuss. ALH bond is highly polar. I already told, right? H minus easily come out from aluminium because of more electropositive atoms in it. So hydride is very powerful and attacks even resonance stabilized groups. Means before resonance, you can see RCOOR, before pi electrons shifting here, the formed positive charge accept H minus ion. That means LiAlH4 will produce H minus faster before resonance. That's why it even reduce these things, right? And coming to next, LiAlH4 reduce acids but not, NaBH4 doesn't. You can also add the same points. Very strong reducing agent, reduce almost all the polar groups. All these things can reduce. LiAlH4 contain high polar ALH bonds, which releases powerful hydride ion. This hydride is strong enough to attack even resonance stabilized carbonyl groups or nitriles. So LiAlH4 reacts violently with water, very important point, and always used in dry ether, very 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 key point this one. Hope it is clear, students. Still I can add few more points about LiAlH4. Why LiAlH4 reduce benzylic compounds but not normal alkenes? So that we will discuss in separate video because it will be more lengthy. So I am going to discuss that in the second video. So must watch. Even you watched by mistake this video, just share your friends or whoever need, because most of the students lose interest about organic chemistry because of these laggings. So one way will say this will reduce, in other way will say this won't reduce. So such confusions all will clear now with this video. Coming to next, Clemmensen reduction, students. Zinc amalgam and HCl. So this also same Clemmensen reduction. What happens, all those things we'll discuss. Clemmensen reduction means aldehyde or ketones converted into respective alkanes in presence of zinc amalgam and HCl. So zinc amalgam and HCl. So this is also called as acidic reduction process because it happens in strong acidic medium. So aldehydes converted into alkanes, ketones converted into alkanes. So esters or acids won't reduce with this phenomena because it's already using acid. So I will tell you what is that. So it happens at strong acidic medium, works only carbonyl group attached to alkyl groups, means aldehyde or ketone. Acid sensitive groups get destroyed, very 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 important here. That based on this multiple times question came in JEE and NEET. So acid sensitive group get destroyed, which means strong acidic medium is required for this. Suppose if the aldehyde, suppose you take this is the, you just take here C double bond O H CH2 NH2 is there. So NH2 is acid sensitive group, students. What it will do, it will take H plus ion from the acidic medium whichever we are using as HCl, means so this NH2 accept H plus and becomes NH3 plus, because between them what reaction happening, acid base reaction. So because of this acid base reaction, the strong acidic medium will be diluted. Because of the dilution, what happens, the strong acidic medium neutralize or become mild acidic medium, that won't support for this Clemmensen reduction. So what we can conclude here, suppose if the same aldehyde or ketone, if acid sensitive groups are present like NH2 or OH, if such kind of acid sensitive groups present, then we preferably reduce with the help of Wolff-Kishner reduction, not with Clemmensen reduction. Same way vice versa in that case, I will tell you why it is. Hope it is clear. Clemmensen reduction happens in strong acidic medium. If any aldehyde or ketone have acid sensitive groups, then we prefer Wolff-Kishner reduction, not Clemmensen reduction, because Clemmensen reduction case strong acidic medium required, which will get disturbed because of those groups. That's all. So coming to this Wolff-Kishner reduction, this is also reduction only, right? Aldehyde become alkanes or ketone also become alkanes. Acid sensitive groups, if it is there over these aldehyde or ketone, then this is the safest method and preferable method. Why it is like that? Because acid sensitive groups is nothing but basic groups only. So occurs in basic medium, so base won't get disturbed. Suppose NH2 is there over aldehyde, so you can take NH2 over aldehyde, then CH2 also, CH2 NH2. If you use HCl in this, so that means a Clemmensen reduction is not preferable, because this group react with HCl and reduce the acidic medium. Instead of that, if you use Wolff-Kishner reduction, NH2 also base, using base, so there will be no disturbance, so it easily reduce. So suitable when acid will destroy the molecule. So acid sensitive groups, if it is there, Wolff-Kishner is preferable. Basic sensitive groups are there, Clemmensen reduction is preferable. Or Clemmensen reduction is also called acidic reduction because HCl is used. Wolff-Kishner reduction we can call it as basic reduction. Okay, so these are the important areas which questions possible to ask. And same way, convert aldehyde ketones to alkane occur in basic medium. Carbonyl group is first converted into hydrazone, which decomposes in strong base to give alkane. So acidic means Clemmensen, basic means Wolff-Kishner. Hope it is clear, students. This is JE favorite. So coming to next, These are normal reduction over metals or metal catalyst, which is also called as catalytic hydrogenation, like nickel hydrogenation of oils or Sabatier's endurance reaction, all will work based on this. So functional groups which are reduced with this phenomena: alkene, alkyne, nitro compounds reduced to specific, like that reduced form. Suppose alkene means alkane, alkyne means alkane or alkene, nitro means NH2 groups, carbonyl means carbonyl generally won't reduce with this, because that we'll discuss. Work by surface adsorption phenomena, that means these metals are having more active sites, it provides surface area for the reaction. So first the metal surface we use, over that we pass alkene or alkane, hydrogen gas, then it start reacting with alkenes or alkanes or nitro compounds. So it works based on the surface adsorption phenomena. Earlier it was worked with H minus donation or medium wise. So reduces pi bonds, not polar sigma bonds. So only pi bonds are reduced, not polar sigma bonds. Reduce pi bonds and not polar sigma bonds. And C double bond O is too strong and polarized. So that will not reduce that easily, because suppose if you use carbonyl compound with metal, it makes strong bonds. So once strong bonds are formed, then it won't absorb hydrogen only. That's why. So what is the main thing in this, students? High pressure specific catalyst, CO reduce. This one rare in JEE exam. Normally it won't reduce, but when they give high pressure specific catalyst, CO also can reduce. So hydrogen with catalyst H2 PD PT and Ni. So in this case, reduce C double bond C and C triple bond C. Also reduce nitro compound, same thing what we discussed here, just to confirm or just to get full clarity. Doesn't reduce these things. Catalytic hydrogenation occurs in the metal surface. So pi bonds supposed to absorb hydrogen from the surface of metal. It's not like directly it will absorb easily on the catalyst, get reduced. So carbonyl bonds not reduced because strongly polarized, so it will give CO minus and C plus. So less suitable for the surface adsorption, so they are generally not reduced. Exam mainly is H2PD prefers pi bonds over carbonyl groups. So wherever pi bonds are there over carbonyl groups, this is preferable. Suppose if you take this one CHO, so this pi bond reduced with this one, not aldehyde or ketones. Hope it is clear, students. Coming to SnHCl and FeHCl, this will work little differently from the before, because here reduction happens by giving electrons, because reduction means adding electrons also, right, or gain of electrons also. So NO2 becomes NH2 group. Here NO2 converted into NHOH, then it converted into NH2. That means what happens, we are removing oxygen slowly by adding electrons. So that's how the reduction happens in this case. So nitro compound converted into NH2, this happens step by step, not directly convert. That's why here oxidation state of nitrogen also you can observe. Here oxidation state is +4, here oxidation state will be 0, here oxidation state will be -2. That means 0 +4 to 0 gain of 4 electrons, 0 to -2 gain of 2 electrons. That's how the electrons slowly step by step it will be added. So electron transfer reduction, it is selective for NO2 groups mainly to convert NHOH or NH2. Coming to this one, same thing, and we can also add some more questions related to this. Why Fe plus HCl is best reducing agent than Sn plus HCl for NO2? Those all I will make as questions and put videos, so watch, surely it will help students. Coming to next, selective reduces nitro groups NO2 to NH2. It doesn't reduce carbonyl compounds. Same thing, electron transfer reduction it is, not hydride transfer. Nitro group easily accept electrons and get reduced to amines. So very selective reaction. It's very selective reaction for NO2 to NH2. And main thing what we have to understand is, selectivity of reducing agent depends on reagent strength, reaction medium, functional group stability. Not all reducing agent reduce all the functional groups. This is the key point which you are supposed to understand. Then only you can work according to requirement. Same way, reduces nitro compounds to NH2, also reduce azo compounds, N double bond N groups, and doesn't reduce these things, same like above, carbonyl and carboxylic acid. So this is not hydride reduction, so it won't reduce these carbonyl or carboxylic acids. It's a electron transfer phenomena. So nitrogen ready to accept electrons, so that reduction happens through electrons for NO2 alone. Iron donate electrons stepwise, tin donate electrons all of sudden, so that stepwise is happening easy to stepwise process is easy to reduce than pouring electrons directly. That's the reason Fe plus HCl is best reducing agent over Sn plus HCl for converting NO2 to NH2 group. This is most important conversion, students, which we have questions. Coming to carbonyl groups, do not undergo this type of electron transfer reduction, so they remain unaffected. Fe plus HCl is highly selective for nitro groups. Very important. So coming to next, diball. There are many reducing agents. All are very important. Diball H, diisobutyl aluminum hydride. This is used in the Stephens reduction. Like, it's not exactly Stephens reduction. Esters converted into aldehydes. So it's a mild reducing agent. Most of the cases, aldehydes are the product with this reducing agent. In Stephens reduction, we use SnCl2 plus HCl. Anyhow, so what work it will do? Functional group and product. Esters can converted into aldehydes. Nitriles also converted into aldehydes. Why it will? Most of the, that's why, what are the products? Always aldehydes are the products. Since it is bulky, isobutyl, diisobutyl. Isobutyl itself biggest group. So diisobutyl hydride is bulky reagent, so it cannot reduce normal aldehydes or ketones. And low temperature is required for this, otherwise it itself will break. Stop reaction half of the way. That's why we are ending with aldehydes only. If it is smaller reducing agent, it can convert to alcohols also, because what is reduction normally? Functional group case, RCOH converted into aldehydes, further alcohols, like that. So reduction means here to here. Why it normally alcohols always give primary alcohols over strong reducing agent. Over mild reducing agent, it will give aldehydes. It won't give ketones in this case. Okay, so this is also very important for JEE questions. Diball has same thing, information partial reducing agent, that's why it stops till aldehydes only. And even PD plus BiSO4 can be used, so that also stops to aldehydes. That is called Rosenman reduction. There is a reason for that. PD or BiSO4 poisons the catalytic activity of PD, so that complete reduction won't happen. So stop reduction at aldehyde stage only, very important point, so that blindly you can remember where diball H is there, that becomes HO, even nitriles or esters. So reduces esters to aldehyde at low temperature only, and nitriles to aldehyde. Diball H is bulky and used at low temperature just to control the decomposition. So it donates only one hydride, prevent over reduction. So it will stop with aldehyde. Exam main thing is diball H gives controlled reduction. Very important. Okay. Coming to next, this is the king of reducing agents, that is red phosphorus and HI. We generally use to convert complete reduction, like glucose converted into N-hexane, students. So it's a very strong reducing system. Convert alcohol or acid or carbonyl to alkanes, directly alkanes only, and removes oxygens completely. This works to remove oxygens. Earlier worked different format. Red phosphorus continuously regenerate HI. So that HI first replace OH of the oxidized form with iodine, then reduction occurs by nascent hydrogen. So if you take any aldehyde group or anything, so what it will do? So red phosphorus plus HI, what happens is this HI make new this will be converted into ROH over reduction. Later Hi is used, this I minus replace OH minus, so which is nothing but normal reduction process, nucleophilic substitution SN reaction, so that Ri will be formed, and finally this produce H minus. I minus is more stable, so H minus should replace I minus and get RH. So that's how the basic mechanism. The OH replaced with I minus through SN reaction, later H minus replace I minus and get respective alkane. So overall effect, CO bonds broken and CH bonds are formed, and this system is strong, that causes complete deoxygenation. That's why even the carbon chain or carbon compound which contain oxygen easily converted into hydrocarbon. Red phosphorus and Hi convert oxygen containing compounds into hydrocarbons. Very very important for JEE or NEET. Coming to next, so this is diborane. Even diborane questions also there in JEE exams or NEET exams. So diborane also reducing agent. So selective reducing agent, but it's commonly reduce carboxylic acids only, because here there is acid base complex is formed, or borane complex is formed, not acid base. Also reduce acid chlorides. So these are the two things reduced with diborane. So don't reduce easily aldehyde, ketones and esters. The reason behind that is B2H6 generally act as Lewis acid due to 6 electrons in its outermost shell, or due to banana bond, all those things. Diborane you have studied, right? So generally BH3 or B2H6 both are having electron deficient nature. So both are need electrons, like electron deficient and Lewis acids. So B2H6 act as Lewis acid base system. Carboxylic acids first form a borate complex with diborane, which makes the C double bond O highly activated. After complex formation only H minus come out from diborane, and that will be added for C plus. Here very simple manner I will tell you. C double bond OH, B2H6 cannot directly give H minus and attacks to this, because this COOH will split into O minus and C plus. So this lone pair of electrons will shift here. So the electrophilicity of carbon in carboxylic acid is less. So what we have to do is, just we have to make busy with this COOH. See what happens is, COOH with B2H6 make borate complex. This is Lewis acid. This lone pair of electron will shift here and get borate complex. So when this complex is formed, what happens, students? This lone pair of electron busy with this diborane, so that this bond always split into O minus and C plus. Somehow the electrophilicity of carbon increases. So other borane molecule produce H minus, that will attack here and reduce the carboxylic acid to alcohol. So aldehyde and ketones do not form such complexes, because aldehyde or ketone doesn't have electron donating groups to aldehyde. See, CHO means this side H, right? It will not give electrons, so it won't react with B2H6 and make complex. Similarly ketone. So this happens only with acids or acid chlorides. Hope it is clear. So this is different way or different mechanism used to reduce it. So B2H6 selective reducing agent for carboxylic acid are this one. So you can see the next one, H2Ni with high temperature. So it reduces alkenes, alkynes and nitro compounds, can reduce carbonyls at high temperature. So same like H2PD, all those things. At what temperature carbonyl groups gain enough energy to absorb on metal surface and allowing reduction. So normal conditions, if you see C double bond O not reduced, and at high, like drastic conditions or harsh conditions, if you use, even C double bond O also reduce with Ni and H2. So zinc and copper alcohols to alkanes happen, convert alcohols to alkanes, used for deoxygenation. So what is another reagent used for deoxygenation? So red phosphorus and Hi. Same way zinc and copper couple. So metal inserts into C double bond CO bond, breaking it and replacing OH by hydrogen. It's less common, but it is conceptual. And the overall, what is the conclusion, students? The main with this is very important. NaBH4 is weak hydride, means H minus weakly come out from this. LiLH4 strong hydride producer, so that it can reduce everything except non-polar alkenes. And NaBH4 reduce aldehyde ketones and acid chlorides also. And one more important thing here you have to understand is, here H2O or polar solvents are required, here dry ether or non-polar solvents are required. B2H6 makes complex acid base complex formation. This reduces acids or acid chlorides due to acid base complex formation. Fe plus HCl is better reducing agent for NO2 to NH2 conversion. This happens through electron reduction process. H2PD surface reduction process, H2PD, Ni, all those things. And red phosphorus and Hi deoxygenation, so it remove oxygens and reduce it. So the overall what we have to understand very important point wise is, reducing agents are selective because each follows different mechanism. Hydride shift happens, electron transfer happens, surface adsorption happens, or complex formation happens. So this is what overall reducing agent and related reactions and mechanisms, students. Now I am going to add few more questions related, like LiAlH4 cannot reduce non-polar alkenes, but it can reduce benzylic or allylic. Why Sn plus HCl is better reducing agent? All, like, there are many models, standard questions only asked in exams. Those things only will keep on continue. And if you want any specific thing, you can comment me, so I can explain all those things. And you can also share whoever need it, and you can subscribe for further videos. Surely it will help for me as well as for you also. Thank you, students. And if anyone need, just you can share this video to them. Thank you.